This lecture is about the structure of the atom, specifically subatomic particles. And our current model of the atom is called the electron cloud model. But as you'll see in the next few slides, we've had several proposed models of the atom over the last 100 years or so. And so we'll kind of walk through the discoveries and how the current model was developed. All right, so an atom, very simply, is the smallest particle of an element that has all of the properties of that element itself. So, as I said before, the discovery of the subatomic particles started the fastest growth toward development of our current model of the atom. Before any subatomic particles were discovered, the earliest scientists believed that atoms were simply like a billiard ball with nothing smaller inside of them. But even that's pretty amazing if you think about it. We can't see an atom with our naked eyes, so the fact that somebody would propose everything's made up of something we can't see is pretty amazing. The first subatomic particle to be discovered is the electron, and that was discovered by Thomson. He used an instrument called a cathode ray tube. It's right here. And that set a current up between a positive and negative charged electrodes. And he used different metals for the electrodes, and he also filled the cathode ray with different gases. And regardless of the substances he used, when he passed a voltage through through that cathode ray, he saw that every substance he tested generated a small particle that carried a negative charge. And so he came to the conclusion then that all matter is made up of these small negatively charged particles, which we ultimately called the electron. So that was the first subatomic particle discovered. So J.J. Thomson proposed that he added to the billiard ball model and said, okay, there are these negatively charged particles that are evenly dispersed. We know they're not now, but he proposed they're evenly dispersed in the atom. And it was also known that overall atoms were neutral. So we knew if there were little negative charges, there had to be an equal positive charge. So he just kind of made the assumption that an atom is kind of overall positive charged. And he called this the plum pudding model, which I guess is easy to see. The next key discovery was made by Rutherford. Rutherford had actually been a student of Thomson's, and his original research set out to verify Thomson's plum pudding model. And so what he did is he took gold foil, just to have a substance that's made up of uniform type of atom, gold atoms in this case. And Rutherford had been working with radioactivity, so he used alpha particles, which you probably haven't learned about, but they are positively charged subatomic particles. And he shot those like a bullet at the gold foil and expected them all to pass straight through. And it turns out most of them did. But every now and then there were some that were deflected, and then even less frequently, there was an alpha particle would be bounced straight back with tremendous force. And so what he concluded then is that there was some region in the atom, in these gold atoms, that was very dense and also repelled positive charge. So he made the conclusion that this very dense area with a positive charge was in the center of each atom, and that when the alpha particles were shot, most of the time they went straight through, that is, if they did not encounter the nucleus. And on the rare occasion they encountered the nucleus, they would be deflected very strongly by both the mass of the nucleus and also by the positive charge of the nucleus. Like charges repel each other, right? And so that was the discovery of the nucleus by Rutherford. And he called his model the nuclear atom model. And just to kind of sum up his findings, most of the atom's mass and a positive charge are located in the nucleus. And most of the volume of the atom is empty space. So he proposed that you have this teeny tiny little nucleus, and the electrons are out here someplace, but most of the atom is empty space. And again, because we knew that atoms are neutral, he said that there were, and we knew about electrons because of Thomson's discovery. So he said there must be as many positively charged protons in the nucleus as there were negatively charged electrons around it. And then just real quickly, they did know what the mass of an atom was approximately, and the protons alone did not account for the entire mass of the atom. So there was a missing piece of mass, which they knew was in the nucleus, and that ultimately was called the neutron and discovered by Chadwick. All right, so the bottom line is, with these key discoveries, is we know that all atoms are composed of the three basic subatomic particles. There actually are subatomic particles, so you can break proton and neutron apart further into quarks, but we won't get into that in this class. Protons and neutrons have nearly identical masses. Proton is positively charged, electron is negatively charged, and neutrons have no charge. So here's a table that kind of summarizes it. You do not need to know the absolute value of the mass of any of these. It is handy to know scientists develop a mass unit of atomic mass units just for things on the atomic scale because they're so small, and who wants to work with numbers on the order of 10 to the minus 27th? But you can see that protons and neutrons both have a mass of about 1 atomic mass unit, and that electrons are less than 1/1000th of the mass of a proton and neutron. So we just assume the mass of an electron is about 0. Again, neutron has no charge, and the proton and electron have equal and opposite charges. All right, so let's talk about the symbolism we use to identify each individual element that we know of. Looking at the periodic table, the most important number is the number on top when it's in the periodic table, and that is called the atomic number, and that tells us the number of protons. And that is the most important number because it tells us the identity of an element. Okay, it is the number of protons. So an element can have different neutrons, different electrons, but it must always have the given number of protons, the same. All right, so elements are arranged in our current periodic table by their atomic number, by the number of protons they have. So hydrogen has 1 proton, helium has 2, etc. You'll learn this again later, but elements that are in the same vertical column, which is a group, we'll learn that again later, have similar physical and chemical properties. We'll learn why later also. So you need to be able to know what all the numbers are for each element on the periodic table. Again, the top number is the atomic number, the number of protons, which is abbreviated with a capital Z. Then there's the chemical symbol. And if the chemical symbol has more than one letter, the first letter must be uppercase and the second letter must be lowercase. So that's important. So if you wrote beryllium like this, it would be wrong. Okay, as I said before, an atom can have different number of neutrons and different number of electrons and still be the same element. But a particular element, let's look at carbon, must always have the same number of protons, which in the case of carbon is 6. So atoms that are the same element but have different number of neutrons are called isotopes. So here's carbon showing its 3 isotopes. So you can see again, since they're all carbon atoms, it should be carbon-12. Since they're all carbon atoms, they all have 6 protons, but the number of neutrons is different. So the top number, and again, this is the opposite of how it's shown on the periodic table. On the periodic table, the atomic number is on top, okay? And then the mass is on the bottom on the periodic table. When it's written on pen and paper, the mass is on top. That's called mass number. And the number of protons or atomic number is on the bottom. And that's for a very good reason, which you'll see in a minute. Okay, so the mass number is the protons and neutrons added together. And that's because if you remember, protons and neutrons both have a mass of about 1 atomic mass unit, and the mass of electrons are negligible. So the mass number comes from the protons and neutrons, the nucleus. And so obviously if you have more neutrons, your mass is going to be larger. And then, of course, that's number of protons. So how do we find the neutrons? The neutrons are found by the mass number, which in this pen and paper format is on top, minus the atomic number. Okay, so A minus Z is the number of neutrons. So that's why when we write the symbol for an element on pen and paper, we put the mass number, the larger number, on top, because it's easy to set this up as a subtraction problem to find the number of neutrons. Alrighty, still talking about isotopes, and remember again, isotopes are the same element, in other words, same number of protons, but different number of neutrons. And one way to show it would be like I showed you with carbon, where you showed this type of symbolism for the isotopes. Okay. And another way is like this, where you have the element symbol followed by a dash and then a number. That number is the mass number. All right. So just be familiar with this. If you see this, that they're showing you a specific isotope of neon. It turns out that every single element has multiple isotopes, which is kind of odd, but interesting. All right, and it turns out that the relative percentages of each type of isotope is different. So, for example, looking at the 3 isotopes of neon, neon 20, so how many neutrons does neon 20 have? You just do the math. 20 minus 10 means it has 10 neutrons. Neon 21 has 11 neutrons. And neon 22 has 12 neutrons, okay? So neon 20 with 10 neutrons is much more abundant in our world than the other isotopes. And so any place in our world that you would gather a sample of neon, if you were to analyze it, each sample you gathered, regardless of where you got it, would have this breakdown of isotope percentages. So one of the first calculations you'll need to get a little bit of practice doing is calculating the average atomic mass. So first of all, I want you to understand what is the average atomic mass, okay? First of all, it shows up in the periodic table at the bottom of each element symbol. The average atomic mass is the average of all of the isotopes of that element. Okay? And it's not just a simple average. Like if I said, what's the simple average of 2 and 4? Well, you'd add them together, right, and divide by how many you have, and you'd say, okay, the average, simple average is 3. That's not the type of average for average atomic mass. The type of average we do for that is called a weighted average atomic mass, and what that means is we give more importance to some of the masses than to the others. So if an isotope is more abundant, we give it more weight in the calculation. So if you look, and you may want to write this down, so what I recommend to students when they take notes is in your notebook, some place toward the end, you have a sheet of paper that just has formulas on it. That'll come in handy when you're studying for a test. So I would jot this down someplace, and it'll help you in your homework also. So the formula for the average atomic mass, okay, is the fraction of that particular isotope times the mass of that particular isotope. And you add that together for every isotope that you have. So if you have 3 isotopes, you're going to have 3 of these things that you're going to add together. So let me talk for a minute what I mean by fraction. So if an isotope like neon is present in 90%, this formula requires that you put a percent in fractional form. So in other words, divide the percent by 100. So the fractional amount for isotope 1 would be 0.90. So the average atomic mass that you calculate will be between the individual values of each mass for each isotope, but it'll be closest to the mass value of the most abundant isotope. So here's an example. I'm going to work this one out for you, and then I'm going to suggest on the next slide, there's another practice one, that you turn the video off on the next slide and try to work it yourself. So magnesium has 3 isotopes also, and their mass numbers are 24, 25, and 26. And the average atomic mass of all 3 of those is 24.305. So write the complete chemical symbol for each of them. So magnesium is Mg. Mass numbers, when you're writing it on pen and paper, goes at the top. So I'm going to put 24 there. Then you would need to look on the periodic table and find out what is the atomic number for magnesium, and it happens to be 12. Hopefully I didn't make a mistake there. And so there is the symbol for magnesium 24, magnesium 25, and magnesium 26. All right, how many neutrons are in each? Well, that's just a simple subtraction problem. There are 12 neutrons in the first one, 13 neutrons in the second, and 14 neutrons in the third. Which isotope is the most abundant? This is a really common question. I see it on tests, I see it on final exams, so pay attention to this. The isotope that is closest in mass to the average atomic mass is the most abundant. So 24.305 is closest to 24. So the magnesium 24 isotope is the most abundant because its mass is closest to that of the average atomic mass. Abundant. Alrighty, so here is a sample problem to calculate average atomic mass. This problem is for chlorine, which has 2 isotopes. And so following the formula that I just gave you, the average atomic mass for chlorine, let's start with chlorine 35. So we need the fraction of it. So you take the percent divided by 100. So that gives you 0.7578. Now you can see sometimes you're only given the mass number. And if that's the case, you can use that for the mass. However, if you're given a more precise mass for that particular isotope, use that. You'll just get a more precise number. So 34.969 is the mass of that particular isotope. Be really careful. I use brackets and parentheses so you do your math right. And then repeat that for each isotope. So the abundance for chlorine 37 is 0.2422, and its mass is 36.966. Okay, and just do the math on this, and I would go ahead and check that out. Make sure you get the correct mass. What you want to do in general in chemistry is when you're doing multi-step calculations, carry extra digits until the very end. So particularly in this case, when you have a difference of like 1/100th or 1/1000th, you don't want to do any rounding yet. So at the end, you should get something on the order of 35.45 units for atomic mass units. And how you can check yourself, go to the periodic table, and the average atomic mass you calculate should match very closely to the average atomic mass on the periodic table. So if you look at the number on the bottom of chlorine, it's somewhere around 35.45. If it's an element, you're not aware of what element it is, make sure that the average atomic mass you calculate is in between the mass values for each isotope. And 35 is in between 34 and 36, so you're good. All right, couple more slides. We've talked about isotopes. Isotopes have different number of neutrons. We're going to talk briefly about ions. Now, ions start to be formed when chemical reactions start to occur. An ion is a charged particle, and ions are formed by either losing or gaining electrons. Okay, so if you remember, in a neutral atom, the number of electrons equals the number of protons. Okay, if you take electrons away, you're left with extra protons, right? So if you remove electrons from an atom, you form a positively charged atom called a cation. And it just a little piece of trivia that'll come in handy as we move on to chemical reactions. Metals, which are located to the left of the periodic table, form cations. They tend to donate electrons during a chemical reaction and form cations. Now, if you add electrons to an atom, you're adding negative charge. So what you're going to form is a negatively charged ion called an anion. And the nonmetals, which are located on the right of the periodic table, tend to form anions. All right, so the periodic table, again, as we get more into chemical reactions, we'll go over this again, but just to kind of reiterate what I said. The metals are, you might remember the stair step on the periodic table. This is it. It divides the metals from the left side of the periodic table from the nonmetals on the right side. And it is the metals that tend to become cations and the nonmetals that tend to become anions. That's it for this first lecture.